Hi, my name is Ben Huston.
Hi, I'm Jason Desrosiers. This is Maintaining JSON Schema at Scale. A little bit about me before we get started. I've been active in the JSON Schema community for many, many years. I'm a core contributor to the JSON Schema specification. I've been working on the Understanding JSON Schema documentation. It has some big improvements recently. You should check it out. I'm very active in Stack Overflow, helping out with JSON Schema questions. I'm also the author of the Hyperjump JSON Schema Validator, a JavaScript implementation. And I've been working with OpenAPI a lot recently, working with their meta schemas and helping out with JSON schema related issues. All right, so let's get into it. The trick to maintaining JSON schema at scale is to treat it just like any other code in your system. All the same rules for maintaining large code bases also apply to maintaining schemas. Everything from consistent code style to good test coverage should be on your mind when working with schemas. Unfortunately, it's not uncommon to see schemas that are hundreds, thousands, or even tens of thousands of lines long. We wouldn't let this happen in our code, and we shouldn't allow it in our schemas either. Throughout this talk, we're going to be moving at a pretty quick pace and not hitting all of the details of each topic. The goal is to introduce enough of each topic for you to know what to look for to go deeper after the talk. So let's start by looking at how schemas can be broken down into reasonable sized chunks. In order to do that, we need to know how schemas are identified and how we can reference them from other schemas. Schemas are identified by URIs using the ID keyword. On the right, we have two schemas, one for an address and another for a customer. We can reference a schema by its URI using the ref keyword. Ref is a relative reference that resolves against the identifier of the schema. On the right, we see how the customer schema uses relative reference to reference the address schema. A lot of people seem to think external references in JSON schema are complicated, but it's actually all standard web stuff. All URI roles and behaviors are defined by RFC 3968, the standard that defines URI. If you get confused, it can help to imagine the schema as an HTML document. The ID keyword works just like the base element in HTML, and the ref keyword is like a normal link. In addition to referencing full schemas, you can also reference subschemas within a schema document. There are two ways to do this, but the one you'll probably use most often is a reference with a URI fragment that is a JSON pointer that points to a subschema in defs. Defs is short for definitions and are used to help organize the schema to improve readability or avoid duplication. In the example on the right, the name definition is used so we don't have to duplicate the subschema for first name and last name. Referencing subschemas with JSON pointers should only be used to reference a local schema. If you expect a definition to be referenced externally, you should give it an anchor and only reference it by its anchor. The most common reason to do this is if you have a schema that holds a bunch of small definitions that are used frequently across many schemas. The schema in this example uses an anchor with the name non-empty string to define a schema for a string that must have at least one character. In the reference, we use a URI fragment with the name of the anchor we are targeting. There's no HTML analogy for JSON pointer URI fragments, but there is for anchors. Anchors are analogous to the ID attribute of an element. There's one difference between how this works and what you would expect with HTML and web browser. Unlike the browser, when a schema is referenced, it isn't expected to be fetched over a network. Implementations are expected to have some way for you to load schemas into a local schema store of some kind. Whenever the implementation encounters a reference, it looks it up in the schema store rather than fetching it from the network. So now that we know how to identify and reference schemas, let's look at how we would organize them. Basically, you want to keep your schemas the same way you organize your code. I like to organize them in a folder that matches the path of the URI used as the schema's identifier with a schema.json extension. All this makes working with schemas nicer, but at the end of the day, sometimes it's necessary to compile your schemas into a single bundle for distribution or some other thing. Fortunately, bundling is really easy, even without special tooling. All you have to do is embed any externally referenced schemas in defs without modification, including their ID and schema keywords. The name of the definition is not used, so it can be whatever you want as long as it's unique. In this example, we just used the URI of the schema being embedded. When ID appears in a subschema, it means the schema represents an embedded schema. Any references will resolve against that ID instead of the identifier of the parent schema. This means that you don't have to modify any references. Both local and external references don't have to be rewritten in any way. Because the embedded schema is its own independent schema, it can potentially use a different JSON schema dialect as the parent schema. In this example, both schemas use draft 2020-12, but that isn't required. You can embed a draft 7 schema if you wanted to. Here's the same example, but for OpenAPI. It works the same way, except you embed your schemas in component schemas instead of defs. Okay, let's move on to another topic, code style. Just like any other code, maintaining a consistent and clear code style can go a long way to making schemas easier to maintain and less bug prone. Take a quick look at this schema. At first glance, it looks pretty complicated. Most people's eyes will glaze over as soon as they see that if keyword. So let's clean this up a bit and see if we can make this schema more approachable. The first thing we want to do is add some white space to help make it easier to identify the main sections of the code. The first section is metadata stuff. As a reader of the schema, I know I can generally skip over this block. The next section contains the most meaningful part of the schema. It should be relatively short so it can be understood with a glance. Any complex part should be moved to a definition and referenced. These definitions should have meaningful names so I know what it does without having to dig into the complicated definition it points to. I know from the name of this definition that if this is a USA address, the state field is also required. I now fully understand what this schema does, and I haven't even read half of it yet. If I need to track down a bug or add a feature in that definition, I can dig into it, but it's nice to have it abstracted away when I don't need it. Okay, now let's look at semantic patterns. There are some keywords that should throw up a red flag anytime you see them in a schema. Next, we're going to look at a couple of keywords I sometimes wish I could use a Jedi mind trick to get people to stop using so much. The first one is using one of for union types. This pattern creates inefficient schemas with bad error messages and should be avoided. Here's an example of a one of with a bunch of alternatives. Remember that one of is an exclusive OR constraint. One and only one of these schemas can pass validation. So even when the validator finds one that matches, it can't stop checking the rest of the schemas. It has to check that the rest fail. That means that it has to check every schema no matter what. The more alternatives, the less efficient the schema will be. But it gets worse. It's not just inefficient, it also produces terrible and confusing error messages. Here's an example schema that describes a JSON instance that can be a car or a banana. JSON schema gives us 2 errors. The first makes sense. It says the model must be a string, but we gave it a number. Then it does something confusing. It also tells us that it's missing the required fields for a banana. We can tell pretty clearly by looking at the JSON instance that the data was intended to be a car, but JSON schema doesn't know that, so it shows us all the errors it encountered while evaluating the one of. Both schemas failed, so both are reasons why the JSON instance failed validation. Imagine how bad this messaging can get if you have a long list of one-ofs like in the previous slide. OpenAPI addresses this problem with the discriminator keyword. You have to add a required property to your instance that the validator can use to determine which schema you intended to match on. Now we end up with just one helpful error message and nothing about bananas. This is much better, but it still has a problem. Discriminator can't change the validation result of one of. It can only be used to provide better error messaging. You still have the efficiency problem where it has to check every schema even when it knows it found a match. The recommended way to define union types is with the if-then keywords. This approach is similar to discriminator in that it requires that you add a property to the instance that will be used to determine which schema to validate against. This schema asserts that if the type is car, then it should validate against the car schema. And if the type is banana, then it should validate against the banana schema. With this schema, we get both efficient processing and good error messaging. Only one of the schemas is evaluated, and we only get errors against that schema. But yes, I hear you. The if-then stuff is complicated, verbose, hard to read, prone to error, and just plain ugly. I agree, but it's the best we can do for now. We've been discussing a new keyword proposal that addresses all of these problems. You might see it as a new keyword in the next release of JSON Schema, or at least as a JSON Schema vocabulary. After spending all that time on why you should avoid one-of, it's only fair we also cover a good pattern for using one-of. The only good use of one-of I can think of is for describing mutually exclusive required properties, but it should be fine for any simple mutually exclusive constraint. Okay, let's look at the next keyword that should send up some red flags. Additional properties is used in a couple different ways, but the most common is to use it to forbid properties that are not defined in an object. Unfortunately, that has some harmful side effects for polymorphism. Here's a simple example of polymorphism in TypeScript. We have a cat and a dog type that each extend animal, and we have a function that takes an animal as an argument. The getScientificName function takes an animal, but can also happily take anything that extends animal. Now let's see how that kind of relationship translates to JSON Schema. JSON Schema doesn't have a concept of inheritance, but you can still extend types using composition. Here we have a cat schema that extends an animal schema using ref. At this point, we still have that polymorphic property we had in the TypeScript example. If we validate that the data passed to the getScientificName function passes the animal schema, it will also accept a cat or any other type that extends animal. Now let's add additional properties false to the animal schema. This will cause the cat schema to fail any JSON instance because it has conflicting constraints. Additional properties is telling us that any property other than species and genus are forbidden. But the cat schema is also telling us that the number of lives property is required. So you can think of adding additional properties false as similar to declaring a class final in Java. It can't be extended. That getScientificName function would now only take an animal. It can't take a cat anymore. So what if we move the additional properties false constraint to the cat schema? We have a similar problem. The cat schema forbids any properties other than number of lives, and the animal schema requires species and genus. There are a couple of ways to address this problem, but the easiest way is to use unevaluated properties instead of additional properties. This is a relatively new keyword that works similarly to additional properties, except it will also take into account the properties declared in subschemas. So the cat schema will forbid any properties other than the ones it declares and the properties animal declares. While this solves the problem we had with additional properties, it still results in the cat schema being closed and not being able to be extended. In cases where you want these schemas to be closed, I suggest writing your schemas so that both an open and closed version is available. In this example, we provide an open version of the schema by default. The cat schema can reference this open version of the schema when it extends animal. Then you can provide an alternate version that closes the schema with unevaluated properties. the closed schema can be referenced instead of the open one when strict validation is required. I said before that additional properties is used for a couple of things. Now let's look at one of those other things. Sometimes we have an object that is intended to be used more like a map. The keys are arbitrary and the values are uniform. In this example, we have some data representing the scores in a gymnastics meet, where the scores object maps names to scores. Often people will choose to define this using additional properties. Because there are no properties defined in this object, all of the properties are additional and will be validated against the given schema. That works fine, but now let's add a feature where if the name ends with a star, it means the gymnast will get special 9.0 club recognition. With pattern properties, we can use a regex to check the property names that end with a star and assert that they are greater than or equal to 9.0. Do you see the bug? If we change Milana's score to a string, we won't get a validation error because additional properties only applies to properties that aren't already declared. Because Milana has a star next to her name, it's matched by pattern properties, and additional properties doesn't apply. Therefore, Milana's score is not required to be a number. This is the danger of using additional properties for object maps. Even though the keyword wasn't changed and worked perfectly before, adding another keyword has altered its behavior. That's why I recommend using pattern properties with an empty regex for object maps. The empty regex will match all property names no matter what other constraints appear anywhere else in the schema. Only use additional properties if you truly expect declared properties to be excluded. If you really mean all properties, be explicit and use pattern properties instead. Okay, we've seen several anti-patterns. Now let's look at a positive pattern. I call this the template schema pattern. If you're familiar with the template method design pattern, it's the same sort of idea. This pattern is made possible by the new dynamic ref keyword. So let's take a minute to see how dynamic references work. Here we have two schemas, a base schema and an extended schema that extends base. Each has an anchor that is referenced by ref. These anchors have the same name, but there's no conflict because anchors are scoped to the schema document they appear in. In the extended schema, the A property will be a number and the B property will be a string. Now let's change these to dynamic anchors and dynamic references. Dynamic anchors are just like regular anchors, except that they remain in scope when you follow a ref to another schema document. And dynamic ref is how you reference a dynamic anchor. So let's walk through validating a JSON instance against the extended schema. Evaluation starts by looking for any dynamic anchors in the schema. From this point, any dynamic reference to foo in the schema or anywhere we get refed to will end up here. Evaluation continues with the first keyword, which is referenced to the base schema. It looks for any dynamic anchors in the base schema and finds another foo anchor. We already have a foo dynamic anchor, so this one will be ignored. When we get to the dynamic reference, it will go to the first place the foo dynamic anchor was declared, which makes the A property a number. If we started evaluation with the base schema, the dynamic reference would have resolved to the local foo dynamic anchor, and the A property would be a string. When it's done evaluating the base schema, evaluation moves back to the extended schema. The dynamic reference here resolves to the local dynamic anchor, which makes the B property a number. This was a strange and meaningless schema, but hopefully it was simple enough to get the idea across, so it makes enough sense when we see these keywords in the template schema pattern. Commonly when writing schemas for APIs, we end up with two schemas per type, one for an individual item and the other for a list of those items. The list schema probably has some common paging controls or other metadata included. Ideally, we want all of our list schemas to have the same structure, but we also don't want to duplicate that structure in every list schema in our API. Here we have a car schema and a car list schema. To reduce this duplication, we can create a generic list schema that any schema can extend, This allows us to make changes to the list schema in one place and have those changes reflected anywhere we have a list of things. But there's still one thing we can't change easily. The card list schema is coupled to the list items property of the list schema. If the name of that property changes, we would have to update every schema that extends the list schema. We can fix that by using a dynamic reference. The dynamic reference in the list schema effectively gives us a slot where an extending schema can inject a schema of its choosing without coupling to any part of the structure of the list schema. Let's walk through the evaluation of these schemas. Evaluation starts in the card list schema and finds the list dynamic anchor. This is where all dynamic references will end up. It then follows the ref to the list schema where it finds another list dynamic anchor, which it will ignore because we already have a dynamic anchor called list. Then it evaluates the dynamic reference, which ends up pointing to the car schema. To finish up, let's review all the things we covered that will help keep you sane when managing JSON schema at scale. The schema should describe one thing and one thing only. Use refs to reference related things. Only use JSON pointers with defs. If you need to reference a subschema, it should have an anchor. Use defs to avoid local schema duplication. Use defs to give names to complex assertions. Use whitespace to help keep schemas readable. Use if-then for union types instead of one of. Provide both an open and closed version of your schema using unevaluated properties. Use pattern properties for object maps instead of additional properties. Use the template schema pattern to extend schemas without coupling. That's all I have for you today. Here's a few links to help you go deeper in your JSON schema journey and maybe learn a few more things about some of the things we covered today. Thanks for watching. Again, my name is Jason Desrosiers, and here are some ways you can contact me or follow what I've been working on. I'm also on the JSON Schema Slack a lot, so stop by and say hi. Hello. Thank you for sticking around and watching, and let me know if you have any questions. All right. I saw a request for access to the slides. I put a link in the chat if anybody hasn't seen that yet. Also, I expect to be writing some blog posts to cover more of this, all of these topics, hopefully in a little bit more detail. And so I'll probably post it on the JSON Schema blog, so keep an eye out for that. One question that somebody might want to ask is that why do I recommend only referencing remote subschemas using an anchor? And that's because we want to be able to distinguish what might be referenced somewhere else within our schema and what's completely local to the schema we're working on. So if I change something that's referencing a definition, then I only have to look in that schema to find any problems that might be caused by that change. But if I change somebody a part of the schema with an anchor, then I know that some unknown number of schemas out there might also be referencing that and might also be broken by that change. So it's just a convention to help us know what's easy to change and what's not. All right, any other last questions? I've also been working on the Understanding JSON Schema site, so go check that out for more information. Let me post that link in here too. And there should be some updates for some of the more advanced stuff coming up pretty soon. All right, got a question. Do you have any recommendations for managing JSON schema versioning? Versioning, we usually recommend to use the ID. So if you have a different version of the schema, then you would create a new schema with a different ID. Obviously, that's something that would be dependent on how often your schemas change. Generally, you would like once a schema is published, it should never change. And then if you have to make a change, you should publish a new version with a new ID. During development, of course, that you wouldn't do that, but yeah, that's the general strategy that I would recommend. Any recommendations for representing language-specific types? I'm not entirely sure what you mean. Okay, I see what you mean. Like in 32 or an unsigned something. Yeah. So one way you could do it is with the format keyword. Format can have custom values. And so you can include like, float 64 or whatever as a format for a number. And that can give your schema that extra bit of information. Ideally, you would define a vocabulary that defines all those extra values that you're using. And so tooling could be built to recognize those things and make use of them. We've been talking about creating a vocabulary for a data definition vocabulary. And that kind of thing, I would imagine going into that type of vocabulary.
Yeah, so that's a good question.
All right. Is there a whip? No, we're just in the very, very early stages of discussing it. Let me see if I can pull up really quick that discussion, and I'll post it in the. And that's about all the time we have. So I'm going to find that link really quick and post it, and then I'll say goodbye. Oh, a couple more questions coming in. Merging objects with Olive. Olive doesn't merge. It's literally like the instance needs to be valid against both of the schemas or all of the schemas, each independently. So merging isn't really a thing. And it's not going to be. It's been discussed to death. Yeah, Shane, I'd love to hear about your use case and what you want to use for that. Oh yeah, Shane shared that JSON schema merge Olive library. I believe that is unfinished, but it's a pretty cool idea. But yeah, stop by the JSON schema Slack or the GitHub discussions, and let's talk more about it. Awesome. All right, I am not finding that link to the data definition vocabulary, but I will, I'll post it in the event section later. So try to look for it there. All right, and then I'll say goodbye. Thank you all for coming, and hope to see you around the community.